Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a recording studio in Zurich. Quick thanks to our sponsors, the National Centre of Competence in Research on Dependable Ubiquitous Automation, the International Federation of Automatic Control, and the IEEE. Our guest today is Aude Billard, full professor at EPFL, the Swiss Federal Institute of Technology in Lausanne. Welcome to the show, Aude.
Thank you for having me.
So, Aude, I definitely had a lot of work in preparing this episode. You are widely recognized as a pioneer in robot learning, but what struck me in reading your story and your biography was that you start off as a physicist. And particularly, you do your first year bachelor at EPFL in 1994 in physics, and then you go further with a specialization in particle physics afterwards at ETH, and then with a master thesis at CERN. So my first question for this podcast would be, what brings the shift to robotics, and why did you move towards the robotics field as a physicist?
It's always a concourse of circumstances. So when I started my master thesis at the European Centre for Nuclear Research, I was tasked to do a lot of statistical analysis. Essentially, what you have to do is to try to find one new particle out of a blur of energy distribution. And the way that physicists used to do it at the time was to use statistical tools, a variety of them, to make out what was a particle from the noise and all the other unknown process that take place when two particles collide. And then my professor gave me a new tool and said, look at this new statistical tool. It's called a neural network. Try it. And I did try it. But at the time, surprisingly, even though neural networks were developed, the theory was developed by physicists, we as students had not been trained on how to run a neural network, how to, what were the theory behind that. So I used it a little bit like a black box, and I did not get such a good results. But I was very interested to understand more that tool. And it turned out that there was a possibility, at the time it was the beginning of AI, and it was very hot, this term of AI. There were two departments, one at the MIT, one at the University of Edinburgh. And I got a scholarship to go to either of the two institutions. I chose to go to Edinburgh because I love Scotland. You're young and you have no idea. You have to understand that 30 years ago, but nobody really cared so much about career and what the stake of institution were. So I went to Edinburgh and the Department of AI, and they were training us on what was called Connectionism. Artificial neural networks, basically, and the like of them, which is very close to physics because this is differential equation to a large extent, especially because there was a strong focus on recurrent neural networks with time delay and time series and their stability. And then among the different classes that they taught us, there was one class which was a novel class which they had just introduced on reinforcement learning with some application in robotics. And this was an optional class, which I took with two friends. And there was a competition. First, we had to build a robot, and we had then to develop a control system to program it based on this connectionist, so neural networks model. So I was more into the control and the, let's say, the programming part of it. And one of my friends was more into building the device, but yet we spent hours. I mean, I think we spent almost 40 hours a week on top of all the rest to just build that robot, control it, and we won in the end. So we were incredibly proud. The team was really proud. And I must say, as a physicist, it was different, right? When you do particle physics, you're one person among many. You follow the trend of 200 years or 300 or 400 years of research. Robotics and AI was different. You felt as if you were doing it all, from creating the platform to creating the theory. That was very appealing. And they offered me a PhD position, so I continued with a PhD at the University of Edinburgh in AI and robotics. That's how I made the shift. The theory of the control was not too far because, as I said, it was differential equation. So I developed it in a recurrent network. So it was quite close. But the application, the fact that you could do that on a real platform, So over the PhD, I did build a couple of robots and implement this on the robots themselves. And that was very enjoyable, I must say.
You have anticipated already a lot of questions that I have for you. This was
I'm sorry.
a fantastic introduction because, okay, first of all, you say, what was your interest in robotics? You motivated why that happened. There was one comment that I had, just because I'm aware of many influential roboticists today that are widely recognized as influential today that passed through Edinburgh in those years. I can think about many names. I don't want to name them just because I don't want to be an injustice towards those I will not name. And so I was wondering what was the atmosphere there around that time, just because it seemed such a special place in such a special moment of time somehow.
Yes, it was. And you know what? I'm just back from Edinburgh because they had the 60th anniversary of the Department of AI, computer science now, informatics actually. So, it's difficult to answer that question, to be very honest, because the ambience is, of course, that of a small group. So we were in the building next to the Elephant House where Rowling, the person who wrote Harry Potter, was writing. And I'm fairly certain that I actually saw her writing because there were a number of writers there. And the building we were in was the almost same building that she had a view on when she wrote Harry Potter. It was a building that had a perfect view on the graveyard, which means that you were seeing dead people every single day. So when you ask me what was the ambience was something very different from Switzerland. Scotland is a beautiful country, incredible. The light, everything is different. People were, and when I visited again, so friendly, so warm, outstanding brains, must say, colleagues I had to talk to, including my advisor, who was a physicist by training, very smart people, very open-minded. There were no boundaries. Perhaps it's also the British way. People were just developing new things. And so, yeah, it was, I don't know what to say. It's it was a mix between, we were working like mad. I mean, I was working 14 hours nonstop. I stopped for only 2 days for the entire period of my PhD. And those 2 days, the sky decided to rain nonstop. So it was almost telling me that I should continue working. But yeah, we enjoyed, I say we, but I enjoyed every single minute of it.
Amazing. So, as I mentioned, you opened up many different directions that I would like to dig a little bit deeper. Something that in any case, I would like to ask you regarding what you just mentioned was basically about connectionism and connectionist models. So maybe we can just explain to our audience what is connectionism and what are, if you want, the ramifications that it has in robotics and artificial intelligence.
Yeah, so the term is still employed. There is still a worldwide mailing list with most of the founders of neural networks. So from Sejnowski to Hinton and all the others, they actually have regular debates on that mailing list. That is also the founding of what used to be called NIPS or NeurIPS now. So this conference, what were neural networks for a long time. So I'm not sure how to answer the question. So what this meant, connectionist means that you're connecting things. And essentially, this is the foundation of neural networks. You go back to the notion of neural networks. There was the idea that you had two neurons that will fire simultaneously. And if they did so, then the connection between the two will increase. And this is known as Hebbian learning, which was proposed by Hebbs. And then from there, the idea was, how do you connect all of those neurons? How do you disconnect them? How do you prune some of the connection? How much of this is done through learning? How much of this is done through evolution? And finally, it also went to how do you model the transmission of information once you have built a connection? Is it done through a continuous differential equation? This is the simplest model, which is called a Leakey integrator. Is it done through spiking neurons? Was also some of the foundation that were developed at the time. There were different ways of modeling it. And of course, you have many more complex models that do represent all the chemistry behind the connectivity across neurons.
This is fantastic. So just because you're touching on so many important questions of neuroscience, and it seems that not just for neuroscience, but also many other aspects, as you mentioned, psychology, dynamics as well that comes from, the dynamics of robots coalesce into this field, which is incredible. So as you mentioned, you did your PhD thesis. You continued with a PhD thesis at the University of Edinburgh under Gillian Hayes. I hope I'm pronouncing it correctly. Also a physicist. And you explore basically the use of recurrent neural networks in the context of learning with robots. So I was wondering whether you can give us an overview about your work at Edinburgh, just because I thought it was incredible just reading about it, on my side at least.
Sure, with pleasure, and you're very kind. Let me try to be brief. Let me first start with the example. It may be easier to explain the motivation. Imagine that you want a robot to teach another robot, or a human to teach a robot a language, which was the first task that we had in mind at the time. This was the very early days of what is called symbol grounding. So you will tell the robot, for instance, oh, move left or move right. This is a composition of two words, move and then left. How would you teach the robot to do that, or how would you teach someone, is obviously by showing. So there was an idea that at the time was already explored by my advisor and Yanis Demiris, who is now a faculty member, but was a PhD student at the time at the University of Edinburgh, and he's now a faculty member at Imperial College. The idea of having two robots following each other. Because when you follow the other, like a child will follow a caretaker, the both of them see the same thing, not necessarily simultaneously. So they explore the world simultaneously, so it's easier to learn. My role, my PhD, was about how do you use then this notion of following or moving together to teach the other. So imagine you have the teacher, the caretaker, who has the child robot following, and the caretaker says, oh, let's move left. So the teacher will start moving left. But of course, there is a delay, because by the time the child starts moving left, it's following, right? There is a small delay. There is a small delay also by the time that the child receives also the verbal input. So how would you then, in an unsupervised manner, associate these two things when the temporal delay will keep changing? Practically, I did build two robots. It was funny, two robots that will actually move in a cage. There was a teacher robot and a child robot. They will follow each other by tracking each other with, at the time we had only infrared light. And each time that the teacher was turning left or seeing any piece of furniture and things like that, it will emit a word. And the word was essentially an encoding in a radio wave that would be picked up by the child. But this temporal delay, as well as also noise in what the child will perceive, because the child is behind the teacher, right? So has a partially obstructed view of what the teacher is showing, and there is also some noise in terms of the perception itself. This is how I came to start from one existing neural network at the time, which was an associative memory, static. Think of it as an autoencoder as we use them now. But static, that means any inputs that appear simultaneously in time will be associated. And needed to create some delay. The notion of recurrent neural network did exist, but only with two special neural networks, which were called the Jordan or Hellman networks. So these were feed-forward neural networks with self-connection on the node itself, as well as connection feeding back to the hidden layer, one or two hidden layers. But there was no control explicitly for this notion of the temporal delay and the noise on the temporal delay. So all the work that I did, the theoretical work in my thesis, was to introduce this notion of robustness in both the delay and the imprecise information, the encoding. It's difficult to explain it without mathematics, but essentially the idea was to be robust. So you will build a differential equation, and it needed to be robust on both the inputs, noise, on the activation of itself, as well as the recurrence that is played back. And then I implemented it for teaching robots just a simple vocabulary. I also implemented it to teach robots things that really have to do with verse recurrence, such as learning how to count, 1, 2, 3, 4, etc. It's natural to have this recurrence and to be able to do addition as well as just a start of multiplication.
I have a lot of questions.
Sorry, it's a long answer.
No. I mean, it was incredibly interesting to follow your line of thought. First of all, I was wondering whether your interest in perturbations was motivated by, let's say, your physicist background, and also a connected question is, in the 90s, the obsession of control theory was really robustness in the sense of, again, robustness to perturbations and model dynamics. So I was wondering whether there was much crosstalk between the two fields and whether these were questions that inspired also roboticists by looking at the neighboring field of control theory.
Yeah, it's a nice question. I must say, in my department, perhaps because it was a CS department, there was not much talk with control people. It was primarily AI and robotics. So I don't recall having explicit feedback on this notion of robustness, but certainly must have been there implicitly in the feedback that I received from my advisor. I don't recall this being said explicitly to me. If you want, it was obvious. If you wanted the two robots to be able to train each other, one needed to tackle this problem. There were a number of people at the University of Edinburgh who were developing new neural networks based on Hebbian learning. So in truth, robustness was core to the theory of how many patterns can you store. It was more about the capacity of the neural network. What we call the capacity is the number of patterns you can store in the memory. It was seen as a memory-based, with also the work of Hopfield at the time. And this notion of robustness was key in the static representation because patterns that you were storing were at times noisy. So the question is not only how many patterns can you store, but how many noisy versions of those patterns could you store? And so I would say it was not, perhaps it was stemming from control theory at the beginning, but what I knew was more it was stemming from this notion of storage function in neural networks from a static case, and I pushed it further for the recurrent case.
Amazing. Okay, just a small clarification, I hope, for our audience. I'll do my best because I'm not an expert in this field, but since we mentioned it already a couple of times, just to say what is Hebbian learning, I would summarize it as cells that fire together, wire together. This is something that we often hear, meaning that the connections are strengthened between neurons, artificial neurons, of course, but probably also real neurons, when they are activated simultaneously. This comes from Donald Hebb, a Canadian psychologist who wrote The Organization of Behavior in 1949, and in an attempt to explain synaptic plasticity. And the other clarification, I think the title of your thesis, correct me if I'm wrong, is Drama. Is that right? Or is this just a paper that follows from the... No, it's wrong as well.
It must be. No, I think it's correct, but I wouldn't be able to cite any title of any of my paper if you ask me.
No, I mean, I
which
did...
by the way, I found that was a weakness because being able to choose a very good title for your paper, it's very important. Again, I never paid attention to that until very, very late in my career.
A skill, an art that one develops.
Yes, it is, because this is the way that people can also find your paper and cite it afterwards. But, all of those things.
So there is also a paper titled Drama, and of that I'm sure because I read it. And it stands for Dynamic Recurrent Associative Memory Architecture. And I guess here dynamic really emphasizes the contrast with static networks, as you were mentioning before.
And that is correct, yes.
And the last question that I have in this context, and of course, I mean, I have many other questions, but is how wide was at the time the field of imitation learning or learning by demonstration, and actually whether you can clarify what is the difference between the two, just because, again, I'm not an insider of this field and I'm just curious.
Okay, so learning from demonstration or imitation learning, I would say imitation and imitation learning was, at least in the circle in which I was, a relatively hot topic, not so much for physicists, but so maybe I should also say that one strength of the University of Edinburgh is that it was very mixed. You had really connection to not just the Department of Computer Science and Informatics, but also with psychology and biologists. So in that context, imitation learning was seen as a very important topic for people modeling animal behavior. And within the same period, for instance, you had the discovery of the mirror neurons, which was a tremendous discovery that touches upon neuroscience as well as behavioral science. And people tried also to understand what these mirror neurons represented, both from a connectionist viewpoint. So why do you have neurons that do So what is a mirror neuron? It's a neuron that activates when... So, okay, what was discovered for people who may not know that in the podcast is that... So you had people who... so Rizzolatti and other colleagues studied the activation of neurons in the monkey brain and observed that when the monkey was seeing someone grabbing an object or when the monkey was grabbing an object itself, the same neurons, plural, will activate in both cases. So it's as if when I see someone doing something, I relate this directly to what I could be doing. With the mirror effect, how do I relate? So that was an incredible discovery on its own. And clearly one wanted to also model this and use this as a way to relate information that we do as humans to the way that we could encode this information in robots, knowing that the two had different bodies. And so this also brought in other questions which are to do with embodiment. Rolf Pfeiffer, who's a roboticist, wrote a lot about this key question. How does the body of the robot influence the way that it acts in the world? So you had a bunch of thought like this where people were moving away from the idea of having simply a robot that was an articulate arm living on its own world, but a robot that needed to start looking and thinking the same way as humans do. And then how do we build this relationship between the human body and the robot body? And so, this was when I reflect back, one thing that I see is that this science was done by very few people. So this is why things were moving fast. It was easy to know every single discovery because there weren't that many publications. And it was easy to track.
Definitely a subject that I will ask you about later. Also, just now, you touch on so many profound questions. First of all, as you mentioned, mirror neurons. Second, the concept of embodied intelligence, if we can call it such. So how intelligence is also shaped by the body in which, I was about to say the animal, but it doesn't, not necessarily the animal, but also the robot are embodied into. I did make a note for our audience while reading one of your papers about mirror neurons, because I did anticipate that we would have talked about it. And maybe just as a small clarification for the audience, mirror neurons, as Aude mentioned, I took a quote from Rizzolatti actually, which says that the interpretation of mirror neurons is that they might be responsible for matching the neural command for an action with the neural code for the recognition of the same action executed by another primate. And I guess, as you mentioned, these questions were really the driving forces when you were in Edinburgh.
Yes, this is an advice I often give to the students who work with me, is to be open-minded, to just think of your PhD or your postdoc as a period of time where you do things for yourself. I was fortunate enough to have had a very strong theoretical training, so I did not have to train myself too much on any of the theories. So I had the pleasure to be able to just on, bedtime reading, if you wish, but to read about psychology, to read about neuroscience. I felt it was fascinating to just also make links between the question that we were asking ourselves when it came to be able to control a robot. Many of the answers could be found in what people were writing about the way that humans learn. Humans acquire knowledge by interacting with the world, how the way that evolution also shape the ability of animals to function in our world. It was as if many of the questions that I was facing in my daily work as a roboticist were receiving part of the answer from other fields. Of course, not technical answers, in the sense that they wouldn't build a mathematical model to explain how this worked, but they already had discussed all the options of how this could be solved or not be solved. So it was, I felt it was fascinating, yes.
So I think we lingered on your experience at Edinburgh for long, and there's a lot to cover as well. So I'd like to move on maybe to the next steps in your career. So after the period in Edinburgh and a short postdoctoral experience, you moved to the University of Southern California, where you quickly become an assistant professor and then basically follow up with the tenure track. And I was wondering, what were your endeavors, research endeavors, of course, in that period of time?
And so when I joined the University of Southern California, first I was working as a postdoc with my amateuric, and then indeed I was promoted. So during that period, I continued on similar line but expanded. The idea was still to work on imitation learning. I was fortunate enough to also be able to work with Michael Arbib, who introduced me to Professor Rizzolatti. There was, again, small world. When I think of it retrospectively, it was incredible that it was so easy to interact with those very senior people. Very, very small world. So we did push forward this idea of using connectionist approach, so neural networks, different level, more biological, to really try to explain mirror neurons, or theory of it at the time. It was known only for the monkey, so more how could we scale that to the way that humans learn to imitate, to do body imitation. So I did build a series of models from controlling the muscles to also modeling the different part of the brain, those that were in charge of the memorization of the pattern, the role of the cerebellum in controlling for the timing. This was stemming directly from my PhD, because there was this key idea of, yes, you do control for time delay, but the question is which then brain area controls for that, and how does this brain area interact with other brain area that are more in charge with controlling for what was called motor programs, which are more known as motor primitive those days. How do you represent the different motor programs, the correlation between controlling the fingers versus controlling the arms versus controlling the legs and so forth. So this was the core of my postdoc, yes.
And this is amazing. Again, you anticipate a lot of the questions that I would have. So I noted down one paper in particular. I wonder whether this is where we can pinpoint in time the development of this model. It's titled A Biologically Inspired Robotic Model for Learning by Imitation with Maja Mataric, I believe. And for me, it was like, in reading this paper, it was very interesting to read about the modularity, if you wish, of all these structures. So you really went down deep into modeling abstractions of the spinal cortexes, the role of the cerebellum, temporal cortex, and basically, as you mentioned, the role of all these, I wouldn't know how to call them, but these elements in motor control. And so the biological inspiration is very clear. I was wondering, in this context, as a control theorist, why all of this modularity? Why does nature, it's a bit of a high-level question, but why does nature organize so much in a modular way? Of course, today we have competing architectures. There is a trend towards end-to-end architectures where we tend not to model everything, but then we incur problems of robustness. So I'm just wondering, what are your thoughts there?
Excellent question. So why does nature do that? It's a difficult question for me to answer. My understanding of what biologists can say to that is the fact that there is evolution behind it. And so naturally, the modularity comes from the fact that some of those structures were encoded into some potential genes. And so some of it is replicated and then reused. So it comes from the very ways in which we construct our both bodies, but as well as our control system, along with also this notion of symmetry and the fact that we have a symmetry across our body, at least in one direction. From a control viewpoint, now that I'm further away from those work in my daily life, it's true that I'm not too fond of end-to-end learning, in the sense that I like to understand. This is maybe the key thing that always drove me in research, and I think this is really what we need to do as a scientist, is always to answer the question of how and why. And for this, we need to understand almost every single step of what we build as roboticists. Clear, if we want to build a robot for it to function as an industry, that's a different question. But if we build it as a scientist, then my quest at least is to understand how we come to construct these competences. So the modularity makes it easier for us to be able to debug, if I may say so, to really understand from step 1 to step N what goes well and what doesn't. So when it comes to control a full humanoid robot, which I also was fortunate enough to be able to do in many different occasions, you need to break this down into subparts. Especially if you control for the robots doing full body manipulation, you have to control for the balancing, you have to control for possibly the locomotion, but also for each of the arm, for the coordination between the eyes and the arms, etc. All of those are different building blocks. And following this notion of modularity that we have apparently in the human brain, I would say this is an excellent example to show how biology can help you design the right architecture, potentially, or at least starting with winning architecture, because it has already deciphered the way that all of those different processes have been not only decomposed, but also, and this is the most difficult part, have been combined. I do remember that when I was working with Michael Arbib, he kept always pushing me back to this very question. It's not just about how you decompose, it's how you recompose. And he was right, because this is the most difficult part of the question. Not only how do you recompose, but how do you modify this composition as you relearn a new skill. And I think this is still we're still far from understanding this well. This is also about key question that we're also addressing at large in the literature nowadays, is this key question of transfer learning. How do you transfer what you've learned from one robot to the other? If we manage to understand this modularity, this recomposability, then we may be able to better understand how to transfer this across tasks, across environment, across bodies. That's at least what I believe in.
Incredibly fascinating. Again, I'd like to pause here because there's, again, a lot of meat on the grill, as they say. First of all, a quick mention to Michael Arbib. I came across him, of course, reading your research trajectory, because you do have probably more than one paper with him, one of them called Synthetic Brain Imaging, Grasping Mirror Neurons and Imitation, which I invite the audience to read. It's incredibly interesting. Just the introduction is, which global brain? I found it very fascinating. So very strongly advised read. Michael Arbib, want to make a quick mention, was a direct descendant, academic descendant of Norbert Wiener. He interacted with McCulloch directly, so one of the most eminent neuroscientists out there. And then he was a postdoc of Kalman, one of the most influential control theorists out there. So I thought it was very, very interesting to read about him. And as you mentioned, also, there are many challenges ahead in the context of imitation learning. Here I would refer the audience to a recent paper that you have on annual reviews of controlled robotics and autonomous systems called Recent Advances in Robot Learning from Demonstration. There will be a link in the description, of course. Aside from the categorization and the strengths and weaknesses of this approach to basically robot programming, there is a very interesting list of important challenges ahead that I wanted to discuss. So some of these are generalization, hyperparameter selection, evaluation and benchmarking, and many more, such as learning from multimodal demonstrations and learning from multiple demonstrators and the interconnection with the cloud. I was wondering, it's always difficult to pick, but what would be the main challenge in your view for the future, or for the near future, if you want, in robot learning?
Okay, in robot learning, but perhaps I'll just bridge back to what we were discussing a second ago. The lifelong learning, framework that was proposed by Sebastian Schun and others is yet hard to reach. So I think this is the most difficult part of where robots. So if it would be wonderful if we were to be able to really address this in a sustainable manner. We see how difficult it is to retrain those large models naturally, because they depend a lot on an extensive amount of data. Problems that we already knew in the 80s is you don't want to forget too much about how much you have to forget in order to learn new knowledge. How do you build from old prior knowledge to acquire new knowledge? How much? And if you do that in a completely black box manner, I fear that it will be even more difficult to know how to address this lifelong learning issue. So lifelong learning is tightly connected to the notion of transfer learning, because if you want to do lifelong learning, you need to transfer some of the information. I also started really emphasizing the fact that transfer learning you may want to rephrase this into 3 questions: what to transfer, how to transfer, but also most importantly, when to transfer and when not to transfer. When is it reasonable to transfer information? When, on the contrary, you need to learn from scratch? All of those quick questions are easy to phrase verbally, But transforming that into an algorithm that is robust, where there is interpretability, where we can also analyze the behavior from a control viewpoint, where we can see that as we add new knowledge, what was deemed to be stable, retain some of the stability. What is the stability we're talking about? Is it a shift in the number of fixed points? Is it a shift in the type of dynamics that we were representing? This is really far from being trivial. But this is the way forward. If we want to have the robot being capable of learning, you don't want them to learn just once and then being deployed. They have to keep adapting and learning. And if you want to do that, then you need to have ways in which you can measure that this adaptation is done at no risk. So I haven't seen much work done on estimating the risk of a machine that is adapting online, aside from, of course, all the adaptive work that is done in control. But what I mean here is really learning from new knowledge, vast amount of multimodal information that is fed to the machine. How stable can this learning be? And how can we then also decide to reject some new learning or some new data because we are not certain of the effect it will have on the entire behavior of the robot? Yeah, a vast question, but to be very brief, the key question is how do you acquire new knowledge? How do you transfer this knowledge? How do you decide not to transfer and to learn from scratch?
And extremely fascinating also because all the key questions that you mentioned intersect so many research fields all at once, basically. And yeah, I'm looking forward to seeing progress in the art of forgetting somehow. I guess at this point in time, more or less, we're situated in the early 2000s. And really, your research spawns in a million different directions, all of which are interesting. And so I will try to open up the stage towards at least as many as we can cover in one episode. One topic that we can talk about is certainly of interest to our control audience is dexterous manipulation. One reason why your research has made a splash, at least in terms of statistics, was a video that I found about robots catching objects in flight that became extremely popular on YouTube, more than 1 million visualizations, and the connected publication became one of the most frequently downloaded documents in IEEE history, at least for that period of time. So this has to do with the subject of object catching in flight. And I wonder whether you would like to talk about this subject a little bit deeper, if you wish.
Sure. So that particular demonstration was actually the result of other work that we had done. So the difficulty when you want to catch an object in flight is that everything takes place very rapidly, and there is, of course, an immense amount of noise going on in both the perception of how the object is flying and where it's going to land and how it's going to traverse the workspace of the robot. And the fact that it's happening so fast made it very interesting to press on one particular form of control, which we were developing at the time, based on differential equation, to make sure that we had a closed form representation and we had stability. So here we were talking about asymptotic stability at a fixed point, and making sure that the stability allowed you to guarantee that you will actually reach targets eventually as it travels through your workspace. So it was emphasizing the notion of bizarrely time invariance. It took us a while to convince reviewers. We had literally battles with reviewers to tell them that, yes, it looks like it's a time-based problem because it flies, so you have to catch it on time, right? And I kept advocating the fact that if you wanted to be robust, you need to use time invariant dynamical system for this, which of course was not natural. So you think, okay, it's, the natural way from a control viewpoint will be to say, oh, okay, I know the dynamics of flying of this object, which is complex. And we're not talking about a ball here. We're talking about typically flying a bottle half filled with liquid. So you have the matrix of inertia keeps changing as the liquid rotates and the bottle rotates on its own as it flies. So very nonlinear dynamics. But imagine you have a fairly accurate model of this nonlinear dynamics. By this, I mean the translational acceleration and rotational acceleration. So you can integrate this forward in time. and get an estimate also with external Kalman filter. You have a model, you build your external Kalman filter based on the noise that you know of your sensor, whatever you use to track this object. And then you have a cone of possibilities that tells you, here is where the object is going to be in your workspace when it comes to travel your workspace. Then we have to ask ourselves, what is the workspace of a robot? And in which dimension are we controlling here? Because we have to catch an object, which, as I said, is not a ball. It's, for instance, a bottle. That means that we've lost one axis of symmetry. Orientation matters, which means that we are not controlling just in translation. We're controlling also in orientation. I'm talking here about the gripper itself. We need to align the hand. So we're looking at a workspace that lives in at least 6 dimensions. In practice, it was even a 9-dimensional workspace, but for other reasons, because we were controlling also for the actual gripper itself, the 3 fingers. And okay, now we have this cone of uncertainty of where the object is going to travel within this 9-dimensional workspace, which is so we need to link the two, right? Because we have the object moving in Cartesian space, which is 6D, but we're controlling in joint space, which is another. Imagine just 6D to 6D, but these are not the same dimension. We need to bridge this. And then we need to get there. And as the object flies, your estimate of where it's going to land keeps changing. So your cone of uncertainty keeps moving in this high-dimensional space. And you need to quickly adapt a trajectory for your robot to catch the object. So it's obviously a control problem. It's a very complex one, because you have the 2 flows that need to meet. And the reason why it's not a time-dependent system is because the 2 move, so the best way is to think of it as 2 sets of ordinary differential equations. You have the one from the object flying, the one from the robot. And imagine that the 2 are now coupled in such a way that they need to meet and to asymptotically converge and meet there simultaneously. And so it's exponential stability for the both coupled system. Then naturally, if your object flies faster than what you thought, you're going to move faster because you're coupled. You're coupled in this differential equation. So using just this notion of differential equation, but time invariant, moving away from time, because if you had time explicit, you will have to recompute time all the time, if I may say so. As your estimate gets better, the time invariance is actually simplifying the task tremendously, as surprisingly as this may appear. But it complexifies the analysis of the coupled system, because you have then to prove that they're both stable and
nonlinear dynamical systems, high-dimensional. Yes. And of course, the computation has to be done in real time in order to be able to actually catch the object in flight, which means it's difficult to do, I guess.
No, the computation is really not an issue, because the 2 ordinary differential equations are based on a small addition and multiplication of matrices, and you usually have no more than 6 to 10 of them. So It's extremely quick. What is actually slow is rather the speed of the robot itself. It's a little bit like the tennis player who needs to catch the ball. The tennis player has to start running towards the ball before the tennis player really knows exactly where the ball is going to arrive, just because the body is slow. So it takes a while to get there. So the biggest hurdle in practice for those tasks is the fact that the platform itself does not have very high torque and high acceleration, but it makes the problem interesting. Of course, you could say buy a faster robot, but the fact that it's slow forces you also to start predicting and have a robust prediction from the very start. Yeah.
Again, this is amazing. And in fact, as you mentioned, so dynamical systems start to surface in your research around this stage, more or less, at least from what I see. Of course, they've been present all the way through the use of neural networks, but an emphasis on also multiple equilibria, for example, of these dynamical systems starts to arise. I noted down also in this respect one concept that I got from looking at some of your recent plenaries, an emphasis on feasibility and not optimality, that I thought was very, very interesting. And maybe we can elaborate a bit about that if you want.
Sure. So again, linked to what we just discussed, there is naturally noise in both perception, but also in the control part. And this is also bio-inspired to some extent. I think the reason why humans are so good at recovering from any disturbance, or from many disturbances on a daily life, is because they have a model of what they can do, what is feasible. And then they move within this range of feasibility. So from a dynamical system perspective, this means that basically you're embedding now your differential equation or your dynamical system within a volume. And this is almost more, it's very important to know what is the volume of feasible states and also those that are infeasible. And so that you bound, in real time, you know that you can switch across any of those dynamics, but you cannot exceed that volume. Anything that goes outside that is infeasible. So feasibility is important, of course, in terms of the path that you can take, which keeps moving. Imagine that you're moving in a crowd, then the feasibility space keeps changing as the path is more or less crowded. And this is, thinking of it is in terms of Cartesian space, Siemens joint space. But nowadays, there is also an interest in representing this feasibility space in parameter space, in the key notion of which set of parameters and which combination of parameters makes the tasks to still be feasible, which combination of parameters makes it infeasible. And being able to build a representation of that can be so useful, so many different tasks to warm start, for instance, MPC problem, because you will directly, what is the feasible space, but you don't know what is the optimality. So at least you start from that region. And then you can possibly locally solve for optimality if need be. But yeah, so often whenever we've used optimization technique in the lab, which we do on a regular basis, the big problem is when the solver tells you it's infeasible. What do you do in runtime? It's bad. So I found that in practice, having this key notion of what is reasonable, feasible, and what isn't is much more important than looking for optimality. Optimality is a little bit the cherry on the cake.
Amazing. Yeah, and I was looking also at many other videos of some of your robots, for example, manipulating glasses full of liquid, similar to the bottle that we discussed before, whose basically dynamics changes as you manipulate them. And of course, I guess also modeling the reachable space of robots in general is, I'm not sure whether it's correct to talk about a combinatorially difficult, but one could model that in probabilistic terms, as you've done in your research. And therefore, what I saw is an emphasis in combining approaches that come from machine learning and approaches of essentially dynamical system theory, or even, if you wish, control. I wonder whether you can say something about that. And what is the importance, if you wish, to combine these two approaches together? What are the best ways forward?
Sure. You mean how to combine best machine learning or AI in general and control theory?
Yes.
Yeah, it's an important question. It's, of course, difficult to answer that question. The way I understand it now, but this understanding will evolve and everybody is moving also in one's understanding of how to combine the two as also machine learning evolves. I see two ways. One, which is done by several groups in the world, is to actually, from the mathematics standpoint, you really look at the control problem and machine learning. Most of those, any machine learning algorithm is usually at the basis an optimization problem under constraint. It's a constraint-based optimization problem. And same for most of the control problem. So basically, mathematically, they're not very far. They just don't optimize for the same thing and they don't have the same set of constraints. So once you've made this observation, it's quite natural to try to then see how can you combine the two, mathematically speaking. How can you, if you're data-driven in your control problem, how much of the traditional way of solving a machine learning program can be put in your optimization? That means you may change the objective function to use likelihood to take care also of representing the distribution of the data and the underlying noise. You may want also to make sure that what you're representing is not just one single optimal trajectory, but maybe a distribution of those, which means that now the representation of the optimization problem is different. It's not a set of time-based control, but rather a distribution of those. And conversely, you take the machine learning problem and you ask yourself, okay, how can I put some constraints that come from control to have some guarantees on the learn distribution of trajectories? guarantees that they all converge to one or a fixed number of fixed point, for instance, or that they don't diverge or they don't exceed a volume, and there are many other aspects to that. So this is at the level of the mathematics. You can start combining the two, but that means to really rewrite and redesign a new constraint optimization problem. The alternative is to take existing solution from both and combine them where they can be combined. Let's say you take control approach. The most familiar one is of course a model predictive control approach. But you use machine learning to inform this model predictive control on a number of things that otherwise you will have to put by hand. It could be the set of bounds that exist. You treat it as a classification problem that you learn from data, and that fix the bounds on some of the constraints of your MPC. You could also use it to learn some estimate of the feasible parameters, as I said before. So the feasibility to warm start, the optimization.
Yeah, I mean, that's incredible. I will link definitely in the description also of the episode many of the recent papers that you wrote about how to combine these approaches. And I personally found particularly fascinating learning different attractors of dynamical systems and combining this in the context of robotics. Maybe since we covered already a lot of ground in this episode, there's one other research aspect that I thought would be interesting to touch on that we didn't touch on in this episode so far, and that's the human-robot interaction that seems to be very dear to your heart, at least through the research that you do. I'm wondering whether you can give an overview of what your research has been in this specific realm.
Yes, thank you for the question. I realized that for a long period of time, the human was the teacher. The human knew everything and was teaching the robots in a way that I was thinking of the human-robot relationship. That's why at some point I wrote also in this position paper this notion of master-slave. And so basically the robot was just following what the human had to say, and the human was super intelligent. And I guess over time I realized that while we could take inspiration from the human, sometimes the robot was better, of course more accurate, had also a different body, would solve things differently. And sometimes the robot will actually really be better. And this is all related to all the work that is known nowadays as shared control. When do you rely on the robot to take decision over the human? Sometimes you have to do that. Think of drones. You cannot control them for every single second because we're slow, and the drone has to take some decision over the period of the flights. And it's true also of human robots. Even if you were to teleport the robot, at some point it has to regain stability on its own. So there is this sharing of competences. So I moved from a teacher driving completely the robot to a robot becoming more and more autonomous, maybe sometimes taking decision and overriding the human decision. And in the end, nowadays, we have been looking also at how the two can work side by side when the human is not programming the robot. It's just, an end user. But this is an entirely different question. There, we want to care about the human. We really want to guarantee that you're not endangering the human life. And this is why in our work, we encompass more and more this notion of safety and guarantees in the control loop, because ultimately we see these robots being deployed in our world, and we want to safeguard humans from misbehaving machines. So it has shifted really the relationship between the human and robots to having them work side by side, and human having very little control over the robots, which is. I actually really like your question, because it allows me to step back and look at myself and see how I've modified myself.
It's always a moment of self-reflection when we're here on the podcast for everyone. And for me, it's very interesting to see also somehow the person behind the scientific curtain. Just maybe a quick comment on the safety aspect, because it's actually becoming, it has become already in the past few years a very popular and important question in control, the issue of safety. The way control people tend to address it recently is to design so-called safety filters, basically ensuring that the dynamics of a robot is invariant if there is a set that is invariant under these dynamics, and so as to avoid imagine obstacles or essentially respect some constraints. And of course, we use our favorite tools that are Lyapunov tools, but also others. I was wondering whether what are the main ways in which robotics faces the issue of safety currently?
Yeah, I don't know if I'm really the best person to talk to that. There are people who have worked on this for much longer than I have. So maybe I could point to work done by Stefano Stramioli and also, of course, Sami Adadin on those. I've seen interesting work, and I would say that Lyapunov, but essentially Lyapunov is energy. So conservation of energy, transfer of energy. You always go back to the fundamental of physics: is how much energy is transferred to the poor human body when you hit the body, essentially. Yeah. So, and how can you guarantee that you're transferring as little as possible, and how you bound this transfer of energy in such a way that it's not detrimental to human will depend on where you hit the human. And there are parts of the body that can absorb more or less energy. So the new trend that goes into really looking at this in terms of transfer of energy, as opposed to just an upper bound on the force, makes sense to me more than just an upper bound on force. Why? Because the amount of time during which you're in contact matters. You can break tissues even with a smaller amount of force, but for a long period of time, you can destroy a tissue. So it's really the entire amount of energy transferred over the period of the contact that matters more than the absolute amount of force. And how to devise control mechanism to absorb some of that in smart manner, be it, of course, with being passively compliant, actively compliant. Compliant means to absorb some of the energy in a directional manner. I absorb this. That means what? But either I deform my body, so I diffuse that within the body of the robot. That would be passive. But if it's active, that means you're gonna move. And the question is, where do you move? Because you need to move in a direction that is safe. You don't want to hit someone else, right? So this calls for new strategies. There are some work, and we've contributed just a little bit on this also. This goes back also to this notion of feasibility. What are the feasible trajectory you can do? And it's not just feasibility in Cartesian space, where in which direction to move, but how fast? Because again, you're going to transfer some energy as you move backwards. So imagine that you're going to start bouncing left and right on different parts of the body. Maybe it's okay. Maybe you bounce, but softly, and then you distribute your energy across different parts of the body that you're hitting. May not be very nice, maybe scary for the human, but not too dangerous. I'm just brainstorming here, but we need to start devising new ways in which we control for that in smarter ways. Yeah. So
it's extremely fascinating, also from a control theoretic perspective. So maybe this is actually a good moment to start shifting towards broader questions. If you wish, I have a small set of questions that I'd like to ask you that are more related to, say, the future, advice to future students, and also your role in the IEEE RAS Society, the Robotics and Automation Society. You're now the president-elect of IEEE RAS. And I found a particularly interesting quote in another podcast where you state that deadline for conference is a mistake. And also you go on speaking about the fact that we have essentially too many publications, more publications that we read nowadays. So I don't know. I wonder whether you have any comments on that.
Plenty for 1 hour talk. So on the first one, deadline forces people to submit things by a certain amount of time. And so it forces people to submit papers when the deadline arrives and not when the work is ripe. This is different. I would like to emphasize that science is about development of ideas and, somehow I will, but maybe it reflects on the way that I function, and I know not everybody functions. So I've seen so many people just being submitted because it was a deadline, obviously, and not because the work was ripe and ready. And somehow it's important to be able to set for oneself one's deadline and to see how your own work progresses and not depend on somebody else to set those deadlines for you. I strongly believe that one becomes more autonomous in one's work and more in charge, and also may enjoy one's work more if you are the one setting for yourself your own deadlines and your own quality metric, as opposed to depend on somebody else setting that for you. Of course, there are always deadlines you cannot avoid, and you're doing a PhD over 4 years, and that's the way it is. But those are long deadlines, and in the meantime, you should set yours. So, yeah, I truly believe that this is the wrong way. Suddenly, I've seen so many people working like mad for 1 week or 1 month to hit a deadline. I don't think you're more productive this way. I truly believe that science is about thinking and thinking about the same problem over and over again, progressing and keeping track of your own progress and pushing you to rethink. I played chess for a long time. The first thing that you learn in chess is to avoid revisiting the same strategy twice, because otherwise you lose time and you're going to lose the game. And I apply the same in science. You progress in your thinking and the way that you try to solve the problem in a systematic manner. So you do for yourself a sort of a to-do list of, I'm going to check this and I'm going to apply this solution, and then this one and this one. And these are the deadline that you set for yourself. This is the path you set for yourself until you solve it. I don't believe that you can do that under a huge amount of stress, not sleeping for 1 week or for 1 month, and trying to meet a deadline. But yeah, and anyway, maybe you want to scratch off what I said. I don't know.
I think it's fantastic, actually. But then a follow-up and perhaps difficult question is, what can we do about it? And an even more difficult question would be, as the president-elect of the IEEE RAS Society, what would you do about it?
Yeah. So this relates also to the second part of your question. We have too many publications. I'm absolutely convinced we have way too many publications, very incremental. If I compare to what I was doing when I was a PhD student, I was able to know almost everything that was published that was related to, but not only related, things that were in different fields, but related to what I was doing. I had the time to read of this because there weren't that many publications. What I see nowadays is that a lot of the PhD students are lost. They don't know, because there is so much being published. Even I cannot cope if I just count the number of papers that are relevant to the research done in my lab, just published in one conference. Let's take ICRA or IRAS. There will be at least 700 or 800 papers relevant just for one conference. Imagine if I had to read all of them. It will take me 2 weeks flat doing nothing else, and I'm kind, and I would not even understand all of them. And there is far more being published, so it's impossible to keep up with the amount that is published. Is it because we've grown so much? I don't think so. I don't think that, and also don't think that the progress in science increases linearly with the amount of money we put in. I know it's debatable. I don't think so. I think we have reached a point where we may want to bend a little bit the growth in funding. Not everybody is made to be a scientist, and it takes time to get results also. That's and it links to the design. So what do I plan to do as a president of RAS is to keep working on emphasizing those points. Of course, it's a collaboration with everybody to try to find ways in which science is still progressing, but we strive for quality and not quantity. Mm-hmm. I would love to see deadlines go, and I'm not the only one. It's something that people have slowly realized that this was an issue. Not having strict deadlines for conferences, because it's also another problem, is that you have lots of people dropping everything that they're doing to review tons of papers in a short amount of time, which does not speak towards the quality of the review. And reviews need to be high quality, papers need to be high quality, and this is conversation between the two. I also dislike conferences because it's a binary process. You submit, it's a 0-1 type of thing. I don't think this is the way science should work. It's more about the journal review process where you give feedback. I've always given constructive feedback when I do reviews. I used to sign my reviews so that people will know who I am. I don't have to hide myself, and we get a conversation going, and I'm here to help you progress in your research, not to discard your paper. So all of these are ideas that I'm trying to, but the way that I approach things is that I try, first of all, to convince people. I don't impose my ideas. This is the way I believe, but if you come with a counter argument, I will listen. And if you convince me, I will change. And you've seen that over this podcast. I've changed over my entire career. I've seen things differently. So But this is a conversation I have with all the people behind RAS, but also with the entire community. We have now town halls at ICRA, IROS, where we engage with the people there, with several hundred of people in the room whom we poll, we ask them questions, we ask them to think about it, to tell us, just allow people to think of there are different ways of functioning. Are you happy with the way it is? Amazing to see the number of people saying that they all got a review from someone who was obviously not knowledgeable. This is awful. This is the end of science. I mean, I'm really very, very scared here, because if you start having people reviewing who don't understand what they review, everybody has wasted time. The reviewer has wasted time, and you have wasted time also submitting your paper. And that also means that some paper may get accepted that shouldn't be accepted, because then again, non-knowledgeable reviewer may accept things that are not publishable. So I truly believe we need to slow down in research and to vouch for quality as opposed to quantity. But I'm here to try to convince people. If people want to do differently, I will go with the majority vote. Very democratic, very Swiss.
Well, first of all, you have my vote, 100%. This is such an interesting topic. I think I should probably devote an entire episode to this at some point, because the problem is evidently there. The types of solutions that many different areas of research have proposed are, of course, different. Some of them might be actually a good idea. I'm thinking about, for example, open review in the machine learning community, where reviews are now online and double-blinded. This is just one way. I've seen other types of conferences that only accept posters, for example, and no papers whatsoever, essentially just inviting by invitation only a certain selected community of people that would actually have something to share. So yeah, definitely a very interesting topic and very important. I tend to close the episode with one last question, which is, what sort of advice would you give to future students, future generations?
Go for science because you're passionate about science, passionate about your topic. So just please yourself during your research. Enjoy it. Do science because you love asking questions and finding answers to questions.
This is amazing. And well, thank you so much for your time. It's been a pleasure. Thanks a lot for your time, Aude. It was amazing.
Thanks a lot, Alberto. Have a good day. Bye-bye.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.